Hello everyone, so my name is Muhammad Saimi. I will be explaining about the circuit design and the specific components that we use to meet the assignment requirement. So for this design, we use the 2N4416 JFET following the assignment guidelines. I have ensured the model parameters are set to an IDSS of 10 millimeter and a pinch of voltage VB of 4V. These values are essential for calculating our Q point later on. We have used a 1 milliohm resistor where this is connected to ground to keep the gate at 0 VDC, which provides the extremely high input impedance that JFETs are known for. This is the source for the source resistor. This is set to 1 kilo ohm. As current flows through the JFET, it creates a voltage drop across RS, making it the source positive relative to the gate. This successfully creates the negative VGS needed to bias the transistor. For the drain resistor RD, this is set to 2.2 kilo ohm. It is where connected to the 15V VDD supply. RD is critical because it converts the GFET's current changes into the output voltage signal we want to amplify. I included coupling capacitors at the input and output to block DC voltages from interfering with our signal sources or the load. I also added a bypass capacitor CS across the source resistor, where this is so important for the AC analysis because it shorts the source resistor to ground for AC signals, which maximizes our voltage gain. Summary of the design goals is where by using exact values 15V supply, 2.2 kilo ohm drain and 1 kilo ohm source, we have designed a stable amplifier where we're ready for simulation and comparison against our theoretical results.
For my part, I will present the simulation results of a common source JFET amplifier design using multisim. The presentation will focus on the DC operating point analysis and the AC signal response observed using the oscilloscope. First, I will discuss the DC operating point analysis as shown on the screen. From the simulation results, the drain current ID is approximately 2.46 milliamperes. The source voltage Vs is around 2.545 volts and the drain voltage Vd is approximately 9.46 volts. Our theoretical value for ID is 2.5 and for Vd is 7 volts. Using these values, the drain to source voltage VDS is sufficient to keep the JFET operating in the saturation region. This confirms that the amplifier is purposely biased and suitable for linear amplifications. This value closely matches the theoretical Q point calculated earlier, with only small differences due to simulation model limitation. For transition to AC analysis, after confirming the correct DC operating point, the next step is to observe the AC behavior of the amplifier. So for the oscilloscope results, now looking at the oscilloscope display, channel A represents the input signal, while channel B represents the output signal. The input signal is a sine wave with an amplitude of 10 millivolts and a frequency of 1 kilohertz. the output signal has a noticeable larger amplitude, indicating that voltage amplification has occurred. For phase inversion explanation, it can also be observed that the output waveform is inverted by 180 degrees relative to the input signal. This phase inversion is a key characteristic of the common source JFET amplifier configuration. For voltage gain observation, by comparing the peak-to-peak voltage of the input and output signals, the voltage gain of the amplifier can be estimated. The simulated voltage gain is consistent with the theoretical value calculated earlier. Any small deviation between theoretical and simulated results can be attributed to non-ideal effects in the JFET model and component tolerance. So for the final conclusion, the simulation result successfully verified the theoretical analysis of the common source JFET amplifier. The DC operating point confirmed correct biasing, and the oscilloscope results demonstrate voltage amplification with phase inversion. So, this shows that the amplifier is functioning as expected and meets the design objective of this assignment.